Hi there, this is Professor Monty. We are going to do something a little bit different today. What I've done for today's lecture is I've already written the notes down, and I actually recorded it as I was writing the notes, but the recording stopped halfway through. So the writing continued, and then when I went to play back to send it out to the class, I noticed that the writing had stopped halfway through. So I'm going to go ahead and just talk over the writing. All right, so anyway, today we're doing sections 9.1 through 9.3, and we're jumping into hypothesis testing. Now, what we had done before, last chapter, we had started on the confidence intervals. And remember, with the confidence intervals, that was really our first step into inferential statistics, where we're using data from a sample to try to predict or infer something about the entire population. In general, last chapter, we were estimating what the mean of the population was, and we were getting a confidence interval, remember, that was centered around the sample average or the sample mean to give with some percentage of confidence where we thought the population average was. Well, now we're going the next step, and we're actually testing to see if the mean is the same as it was, different than it was, less than or greater than what we might have thought either it was in the past or comparing it to some number. So that's what I've written down here. So as we go through, I will just explain what I wrote originally. So with a hypothesis test, we've got two hypotheses. We've got the null hypothesis. So here, we will jot this down as 1. We've got the null hypothesis. The null hypothesis denoted H sub 0, and that's the hypothesis we're assumed to be true. Typically, they refer to this as the status quo hypothesis. So whatever we're looking to see that the mean has done in our case, we're going to see if it's changed, how it's differed, but we're always going to assume that it hasn't differed. Notice I wrote that we always include an equal with the null hypothesis. For example, the null hypothesis might be that mu, the population average, is 75. Say that was the population average maybe on the first test. We're looking at the second test. We don't have all the data for the second test. So what we're going to do, and by test, I'm referring to like an exam in our class. So say the exam average on the first test was 75. The next test, second test, we take it, and we don't have all of the data, but we have a sample of the data, and we want to say, hey, based on this sample, does it look like the average is still 75? So the null hypothesis will be that, yes, it's going to be equal to 75. The alternative hypothesis, denoted H sub A in our book, a lot of books denote it H sub 1 so that it doesn't look like a 0. But our book uses the H sub A. That's the hypothesis we're trying to show. So the question may be something like, hey, has the average changed? The average on exam 2, is it different than the 75 on exam 1? So notice here, so here's my second hypothesis, the alternative hypothesis. Those are the two that we can have. So there's 3 possibilities. A, the alternative hypothesis could be that mu is not equal to 75. So it's changed from 75. Maybe we say that the question is it different from 75? B, the second possibility, is maybe the question says, is the average on exam 2 less than the exam 1 average? Or maybe they'll use the word decreased. And then lastly, we'll denote that as C. The question may say, is exam 2 average greater than the exam 1 average of 75? So the alternative hypothesis would be mu is greater than 75. Increased is another word they may use for greater than. All right, so the null hypothesis, again, always has its equals. The alternative might be not equal, might be less than, might be greater than. But in all 3 cases, notice that we're talking about mu, the population mean, not the sample mean. Okay, that's really important. Now, another important thing is the null hypothesis and alternative hypothesis are part of every hypothesis test. So if you don't include them in a hypothesis test, you're going to lose points. All right, so anyway, let's go down to an example straight out of the book, problem 915. It's on page 375. And it asks a question. I will go ahead and read the question for you, but I've got the page number there in case you want to refer to it later. All right. So here's the problem. On 915, the problem says this. And you'll recognize this. This is a problem we did confidence intervals on, but it's toxic mushrooms. Cadmium, a heavy metal, is toxic to animals. Mushrooms, however, are able to absorb and accumulate cadmium at high concentrations. The Czech and Slovak governments have set a safety limit for cadmium in dry vegetables at 0.5 parts per million. M. Melger et al. Measured the cadmium levels in a random sample of the edible mushroom and published the results in the paper, Influence of Some Factors in Toxicity and Accumulation of CD from Edible Wild Macrofungi in Northwest Spain. A hypothesis test is to be performed to decide, now here's the question, whether the mean cadmium level in these mushrooms is greater than the government's recommended limit. So what I wrote down is the mean cadmium level greater than the government limit. And remember, the limit was 0.5 parts per million. So we need to do both the null and the alternative hypotheses. The null hypothesis, again, is always we're going to assume that it's equal to whatever number they say. So in this case, the population mean mu is equal to 0.5 parts per million. The alternative is the answer to the question. The question was, is the cadmium level greater? So the alternative hypothesis is mu is greater than 0.5 parts per million. And so it's simple as that as far as setting up the null and the alternative hypothesis. Let's look at another one to get a little more practice on this. And again, this is a problem we saw in the last chapter that we actually did a confidence interval for. But it's gray seal nursing, problem 916. It's also on page 375. It says gray seals are one of several types of earless seals. The length of time that a female gray seal nurses her pups is studied by S. Twist et al. In the article Variation in Female Gray Seal Reproductive Performance Correlates Proactive Reactive Behavioral Types. The average lactation or nursing period of all earless seals is 23 days. A hypothesis test is to be performed to decide whether the mean lactation period of gray seals differs from 23 days. So I wrote down the key question: does the lactation period differ from 23 days? And so our null hypothesis is going to assume that it is 23 days. And so the null hypothesis, H sub 0, population mean mu equal 23 days. The question says, does the lactation period differ? In other words, is it different? So we put as the alternative, mu is not equal to 23 days as the alternative hypothesis. Because if it's a lot less or a lot more, we're going to say, yeah, it looks like it's different. It's not equal to 23. I don't know if it's more or less. That's not my concern at this point. We may look at that later, but the alternative hypothesis this time would be mu is not equal to 23 days. So that's how you set up the null and the alternative hypotheses. And you'll get some practice of this when you go into the homework. All right, now there's going to be two types of conclusions that we can have. When we get to the end of our hypothesis test, we're either going to reject the null hypothesis and answer something along the lines of, yes, it appears the mean lactation period is different than 23 days. The other type of conclusion is we do not reject the null hypothesis. And in that case, we'd say, no, the data is not sufficient to show the mean lactation period is different. Notice in both conclusions, we always state the conclusion in terms of what the alternative hypothesis was. We don't state it in terms of the null. We never say, for instance, on number 2 here, we never say, oh, do not reject the null hypothesis, and then say something like, it appears the average is 23 days. We can't prove that the average is 23 days. The only way we could prove that is if we had the entire population. And we're only going to have a sample, so we're not going to be able to ever say, yes, it looks like mu is equal to any number. Almost all of the time, we're going to have some statistical variance between our sample mean and our population mean. So say we got the sample mean for this and it was 22.6 days. Well, that can't prove that the average is actually 23 days. So even if we got exactly 23 days as our sample mean, it still doesn't prove that the population mean is 23 days. So with our conclusion, it's always in terms of the alternative hypothesis. Either yes, it looks like the alternative's true, or no, the data is not sufficient to show the alternative, whatever the alternative hypothesis happens to be. All right, now we have an issue that we run into though. Since we're only looking at a sample, we never know if our conclusion is actually true. We may have an error. So we're doing the best we can, but notice we're never going to know if we came to the right conclusion or not, because we're basing our conclusion on the sample. And if we had all of the population data, it may have come to a different conclusion than what we came to. So we may have made an error. And there's two types of errors that we might run into. Notice they're written in Roman numerals. Type 1 error, that's if we reject the null hypothesis when it was actually true. The probability of this is what we call alpha. Now you may recognize that alpha. That's the same alpha we saw when we were doing confidence intervals. And we talked about, for instance, a 90% confidence interval gives us an alpha of 10%. Well, that 10% is the probability that we're false or that we're wrong. Well, if that's the probability we're wrong, that's what this is saying. We reject the null hypothesis when we shouldn't have. The other type of error is a type 2 error. And that's if we don't reject the null hypothesis when it was false. We should have rejected it, but we didn't. And the probability of this is called beta. We don't ever know what the value of beta is. It's referred to as the power of the hypothesis test. And there's ways to calculate beta, but it's nothing we do in this textbook. It's more advanced statistics. So at this point, we're just going to refer to it as beta. And notice there's kind of a game going on between the alpha value and the value of beta. Because if we want to make alpha really small so we don't reject the null hypothesis when we're not supposed to, then beta is going to be larger because we'll accept more things that we shouldn't have. So to make alpha small, beta has to get big. And to make beta small, alpha has to get big. So we have to play with how important is it to us to make sure we don't reject something incorrectly. In other words, how important is it to make sure we don't make a type 1 error? All right, so let's look at a couple problems in this regard. So 923 refers back to the cadmium levels in the mushrooms. And we had a null hypothesis that mu was 0.5 parts per million and an alternative that it was greater than 0.5 parts per million. And this problem, and you'll notice I have parts D and E. I've skipped A, B, and C because I don't think they're as relevant right now to the discussion. But these two, I really wanted to focus on. You're going to see things like this on the exam. So I would imagine you'd like to focus on it as well. But on this problem, they say, okay, those are our hypotheses. Suppose we come to the conclusion that we do not reject the null hypothesis. So think about it. If we're not rejecting the null hypothesis, then we're saying the data is not sufficient to show the alternative that it's greater than 0.5. So it might be 0.5. We just know it's not strong enough to say that it's greater than 0.5. All right, so we didn't reject the null hypothesis. If in fact, again, we don't know this, but if we had all the data, we would see that the cadmium level average was 0.5 parts per million. If we didn't reject the null hypothesis, we made the correct decision. Because by not rejecting the null hypothesis, in that case, we're saying, look, now be careful. We're not saying that mu is equal to 0.5 parts per million because we can't prove that. We're just saying the data is not sufficient to show that it's greater. And in part D, they're saying, look, mu is equal to 0.5. So we shouldn't reject the null hypothesis. You should say, oh, yeah, it might be 0.5 parts per million. I don't have enough evidence to say that's not true. The second one says, well, what if in fact the cadmium level exceeds 0.5 parts per million? Well, if it exceeds 0.5 parts per million and we didn't reject the null hypothesis, again, we're saying that might be true. We should have rejected it if the cadmium level did in fact exceed 0.5 parts per million. So in that type of case, we made an error. Notice we didn't reject the null hypothesis, so it's a type 2 error. A type 2 error is if we don't reject incorrectly. A type 1 is if we reject the null hypothesis incorrectly. So in this time, we didn't reject it. That's what they said here. Do not reject the null hypothesis. That was wrong. We should have rejected it if, in fact, it exceeds 0.5 parts per million. So that is an error, and it's a type 2 error. All right. Here's the other one. So this was the lactation period of the gray seals. The null hypothesis of mu equals 23 days. The alternative not equal to 23 days. This time they say, suppose we reject the null hypothesis. So our conclusion this time, if we reject the null, we're saying, hey, I don't think that's true. So we're going with the alternative. And the alternative, mu is not equal to 23 days. So we're going to say, okay, well, let's see. If in fact mu is equal to 23 days, and my conclusion is it's not equal, that's an error. I rejected incorrectly. It's a type 1 error. Okay, and conversely, if in fact mu wasn't equal to 23 days, oh, that's what my conclusion was. When I rejected that it was equal, I went with the alternative that it was not equal, and I was right. So that's a correct decision. So work with these, get some practice there to see how you're doing. Okay, you'll get some practice with that in the problems in the homework. So don't worry about that. So that's the end of 9.1. Let's flip over real quick to 9.2. And in 9.2, this is where we start hypothesis testing. It's called the critical value approach to hypothesis testing. And I will tell you, this is a common way to do hypothesis testing in schools, in statistics classes, but it's not a common way that they do it in industry or in the research. When I was doing research for my dissertation to get my PhD, every study I looked at that did a hypothesis test did not use the critical value approach. They used the p-value approach, which we'll learn in the next section. But there's a couple things I want you to get out of this approach. All right. So first of all, notice we start again with the null hypothesis and the alternative hypothesis. That always has to be part of the hypothesis test. I'll be more specific next section about what has to be in the hypothesis test, but those always do have to be in the hypothesis test. So let's look at a bell-shaped curve. We're going to learn in order to do these tests, it has to be normally distributed. So say we've got a bell-shaped curve. It's a nice normally distributed population, and we're testing to see if the mean is 23. Well, if we get values that fall a little bit to the side of 23, a little less, a little more, then we're going to say, you know what, that might just be sampling error. Remember, sampling error is the difference between the sample mean and the population mean. And we expect there to be some difference there. Just because when we take a sample, we never expect the sample mean to exactly be the population mean. We expect it to be pretty close, but it might differ a little bit. Might be the same, but there's a good chance it won't be exactly the same as the population mean. But if the value falls really far, so if I go way out here to the right or way out here to the left, if the value falls in one of those two regions, then I'm going to say, hey, you know what? I think that it's too far away. That can't be just due to sampling error. And if it falls out there, we're going to do what we call reject the null hypothesis. And we're going to say, hey, look, you know what? I don't think that the mean is 23 because my sample mean is too far away. And notice this distance here, that's actually what our confidence interval was. So if we get a sample mean that falls outside of if the population mean, rather that they're talking about, falls outside of what we have as our sample mean for our confidence interval, then we're going to say, hey, it's outside of our confidence interval. I don't think it would be out there if the null hypothesis were true. So I don't think the null hypothesis is true. So anyway, we call those the rejection regions. We're not going to actually have these pictures when we do the hypothesis test in the next section, but I wanted to show you this because what they refer to this as, because if the value falls too far above, so over here someplace, or too far below over here someplace, either way, it's too far away from 23, we think the mean isn't really 23. They call that a two-tailed test. And so a two-tailed test is anytime you have a not equal, because if it falls too far to the left or too far to the right, we're going to reject the null hypothesis that was actually equal. All right, now let's look at the second one. If the alternative hypothesis is that mu is greater than 23 days, if we get a value that falls a lot less than 23 days, so we have something over here, I'm not going to reject the null hypothesis because it doesn't look like it's greater than 23 days. We may say, oh, well, it's a lot less than 23 days. It's clearly not greater. If that's all I'm testing, I'm not going to reject the null hypothesis because it doesn't support my alternative that it's greater. So greater is only going to be if it's over here, far to the right. And so that's called a right-tailed test. Anytime the alternative is a greater than, you have a right-tailed test. And similarly, let me erase this, make this look a little more like a, anytime we have a less than, we're only going to reject if the value falls way over to the left. And in that case, it's obviously called a left-tailed test. So I'm going to erase this spot here as well. But so the idea is with a not equals, it's going to be a two-tailed test because either to the right or the left, it falls too far away, we're going to reject the null hypothesis. For a greater than, we're only going to reject it if it falls to the right. So it's a right-tailed test. And for less than, only if it falls to a left. So a left-tailed test. That's what I want you to get out of this section, is just the idea of what side the tests are, what we're doing. In fact, the value that we find here, that area, is actually what we call the p-value. We'll talk about the p-value in the next section. If we were technically doing this as a critical value, we would actually find this critical value here from a table. And then we'd see if our value falls over in the area where the p-value is. So this area being the p-value isn't technically from the critical value over, it's from what we find as from our data. The number is called the test statistic. So I'm actually going to erase calling this the p-value. I'll talk about more of the p-value when we get into that section. All right, so we'll define that. In fact, we'll go there right now. All right, so let's go into 9.3. We'll zoom that back up for you. So 9.3 is called the p-value approach to hypothesis testing. All right, again, let's look at our null hypothesis. Let me make that look a little bit more like a null here. So my null hypothesis, mu equals 23 days, the lactation period of the gray seals, versus the alternative, which is what I'm trying to show, that we think it's greater than 23 days. So what we're going to do is we're going to find our z value. And our z value, remember, is taking our data, whatever we get as our data, our x bar, our sample mean, we're going to use that with what we have as the population mean, which we're assuming to be 23. And then we're going to divide it by sigma over the square root of n, the population standard deviation over the square root of the sample size. That's going to give us some number. The area past that number, that one is technically what we refer to as the p-value. I'm going to write it here and then erase this one I had earlier. So that area past this number, that number is this number. The area past that is technically the p-value. And what that p-value is, that's any value from that number on gives us a certain probability. And so I wrote the definition of the p-value. The p-value is the probability we would get our sample results by chance if the null hypothesis were true. Now, it's that value or more. Right here on the line is that value, but anything past is anything more. So things more extreme. Now, if you go to my YouTube channel, which is just, let me jot it down right here. So if you go into YouTube and you go under Professor Monty, oops, it'd be nice if I could spell it. and I'll send you a link to this, but if you go there, check on my YouTube channel, I have set a slideshow, just a real quick slideshow that talks about what the p-value is. And I've also done an explanation of that same slideshow as it goes. So instead of just looking at the slides, a really quick, I think it's a 20-second video, there's one where it's about a 3-minute video where I explain as I go through the slides. I think looking at that will be really good. And in fact, what I would suggest is if you have certain things you want me to post on my YouTube channel, like how do you do a z-test, how do you find a t-interval, those types of things, go ahead and suggest those to me, and I'll post individual videos, nice short videos of specific things you guys want to see. All right, but I would recommend you go there. It is very important that you understand this idea of the p-value. And I'll explain it as we go throughout pretty much the rest of the semester as well. But remember the definition, p-value. P stands for probability. The probability we would get our sample results by chance if the null hypothesis were true. Now, on my slide, I'm more formal about it. I say our sample results or something more extreme by chance, because our sample results would just be up on this picture, just right at this line. But or more extreme is everything out past there as well. Technically, that's what the p-value is. It's that whole area. Okay, so what's too unlikely? Well, when we're talking about getting our results by chance, if we get something that this happens 80% of the time, we'd say, well, okay, that I can accept as something that would happen often enough. What we're really doing with this hypothesis test, and when we're looking at the p-value, think about somebody telling you a story and you're trying to decide whether that's true. Now, and if you're talking to somebody, you'd say, yeah, it's pretty likely that would be true, then you would accept what they say. But if it's too unlikely, you're going to say, you know what, I don't think that's true. That seems too unlikely to really have happened. I don't think that's true. That's what we're doing with the null hypothesis. We're saying, how likely is it that I would get my sample results if the null hypothesis were true? And if it's too unlikely, then we're going to reject the null hypothesis and say, I don't think it's true. Well, that's why I say, what's too unlikely? Well, typically we go between about 1% and 10% as our cutoff. And we say anything below this is too unlikely. Now that's called the significance level. That's the alpha we were talking about before. Your significance levels will always be somewhere between a 1% and a 10%. Usually they use 5%. If you really want to make sure that you don't reject something incorrectly, type 1 error, if you really are careful about that, you may go down as far as 1%. If it's not that important to be wrong, then you go to 10%. Because remember, if I have a 10% chance of making a type 1 error, I have a greater chance of making a type 1 error. The advantage to that is I have less chance of making a type 2 error. So that's where we have to do that little dance and figure out where we should set it. But 5%, I'm going to make this 5 look a little bit better. 5% is usually our standard. They call it the significance level. Again, it's how likely we are to make a type 1 error. Remember, that's alpha. Alpha is the probability of making a type 1 error. All right, so if the probability of H sub 0, the null hypothesis being true, is less than 5%, we're going to reject the null hypothesis. That's what a significance level of 5% would say. Remember, that's our cutoff, would be 5%. All right, so here's the rule. If the p-value is less than or equal to alpha, then we say, oh, that's too unlikely to have happened by chance. We reject the null hypothesis. Otherwise, we don't reject it. And then the little mnemonic saying to help you remember, if p is low, the null must go. All right, so remember that. If p is low, the null must go. So here's the steps to a hypothesis test. So formally, you need to state the null and alternative hypothesis is always your first step. Make sure you do that, because if you come to a conclusion and you say reject the null hypothesis, but you never told me what the hypothesis was, I don't know what you're talking about. So do make sure you do that. The second step, determine the significance level alpha. Now that's going to be given to you in the problem because there's no way you could determine it by yourself. Again, if it's not given, we usually default to 5%. All right, then we're going to actually calculate or find the p-value. Now, when we find the p-value we're going to find using our calculator. So don't worry about that. Let me shut that down real quick. So the p-value, we're going to find that on our calculator. Then we come to our decision rule. And the decision is, should I reject the null hypothesis or not? Again, it's going to be based on the p-value. We'll see an example of that shortly. And then lastly, state my conclusion. The conclusion is always an answer to the question. It starts with yes or no, and then you state your conclusion in terms of the alternative hypothesis. But notice, in terms of the alternative hypothesis. We'll show that as we do a couple examples. All right. So let's scoot on from there. Let's go to an example. All right. So suppose the significance level alpha is 5%, 0.05. If we calculate a p-value of 0.02, remember what that significance level of 5% means. It means if I get something that happens less than 5% of the time, that's too rare, I'm going to assume the null hypothesis is not true. Because remember, the p-value is the probability that it's true. And so if I set my significance level alpha at 5%, but I get a p-value of 2%, that's less than that 5%. I would suggest the easiest way to remember the p-value. Now, this isn't technically the definition, but a good way to remember it is the p-value is the probability the null hypothesis is true. So if you think of this p-value as the probability the null hypothesis is true, we'd say, hey, in this case, there's only a 2% chance that the null hypothesis is true. That's less than my 5%. So in that case, I'm going to reject the null hypothesis. I don't think it's true. My cutoff was 5%, and there was only a 2% chance that the null hypothesis is true. So I'm going to reject it and go with the alternative. All right, another example. This time, alpha is 5%. So we have a 5% significance level. We calculate the p-value, and the p-value comes out to 0.27. Well, that 0.27, notice that really means 27%. So think, oh, there's a 27% chance that the null hypothesis is true. That's a lot higher than my 5% alpha. So in that case, my decision, since the p-value is 0.27, notice what I did here. I'm going to redo it for you. So I start off with the p-value of 0.27 less than or equal to 5%, which is alpha. And I say, wait a second, it's not less than or equal to that, so I'm going to cross it out. Since it's not less than or equal to, I'm not going to reject the null hypothesis. There's a 27% chance that the null hypothesis is true, which is much greater than my 5% chance. Since it wasn't less or equal, I'm not going to reject the null hypothesis. I like to do up here a less than or equal to, and down here a not less than or equal to, because then I only have to remember one formula. If the p-value is less than or equal to alpha, I reject. If it's not, I don't reject. And so that's how I came to those conclusions there. And look at that. We have come to the end of the 3 sections. Hopefully that worked for you. And I will tell you what I'm planning on doing is I'm going to do one this way for you. I'm going to do one where I write the notes as I go, and I'm going to do a lecture where I lecture on a whiteboard. And then I'm going to give you guys a chance to vote on which way you think is most effective. And if overwhelmingly it's one over the others, then we'll do that as much as possible. All right, hang in there, study hard, stay healthy, and hopefully we'll be back in class soon. But practice these things, get your homework done, and remember, you can do this.